Welcome back all of you. So continuing with solar energy part, mainly solar geometry and solar radiation. So in previous class we had seen different angles that are used in the solar geometry to calculate solar radiations and along with latitude and longitude and the concept of peaks and hours. So in today's lecture we will cover different types of solar radiation and different instruments that are typically employed to measure different types of solar radiation actually. So, types of solar radiation, there are mainly three types. If you have the sun whose radiations are falling on the surface or on the ground, some radiations they reach directly onto the surface, which are also called as direct radiation or beam radiation, because they do not change their direction, they come straight from sun to the surface. Then there are some radiations which get scattered here and there because of the clouds and particles in the atmosphere, the water vapor, the gases, and from those the diffuse radiation make its way to the surface. So that's called diffuse radiation. Okay, it doesn't travel in the straight line and it frequently changes its direction. And then some part of the radiation comes from the reflections, like because most of the time the surfaces receiving radiations are tilted or at certain angles. So when radiation strikes the surface of the ground or any other objects on the ground, they may get reflected to the surface. Though the portion of this kind of radiation is typically low compared to direct and diffuse, but it does occupy certain percentage of the total radiation. So those are the three types of radiations which are defined now. So direct radiation or beam radiation, it is solar radiation that travels in a straight line from sun to the earth's surface without being scattered by the atmosphere. Atmosphere is always there, but not all the radiation gets absorbed or scattered by the particles in the atmosphere. Some of it reaches in a straight line to the surface, and that's called as direct radiation, beam radiation. It is this direct or beam radiation which is responsible for most of the energy that we get from the sun after collecting. Diffuse radiation, it describes the sunlight that has been scattered by molecules, particles and dust in atmosphere, but that has still made its way down to the surface of the earth. That is the diffuse radiation. Reflected radiation, the portion that is reflected back from earth's surface, mainly ground, water, buildings, snow, towards the surface that is receiving the solar radiation, mainly like solar panel or solar collector. Hence, if you have a surface which is horizontal, if this is the ground, and on the ground if we have a horizontal surface, in case of horizontal surface, the amount of radiation that is received by reflection would be negligible. Okay. So, for a horizontal surface, reflected radiation is negligible. So, we would get only beam and diffuse radiation and no reflected radiation. Hence, it is negligible for horizontal surface. Asphalt has reflectivity of 4%. Lawn reflects around 25% of the radiation that hits it. So, total solar radiation, or sometimes it is called as global solar radiation, it is the addition of all these three components: diffuse, reflected and direct. So, now let us look at like how does this radiation vary with respect to different surfaces. Okay. So, before that, just a quick comparison. The direct or beam radiation comes directly from sun, and more clear is the atmosphere. There are less clouds, less particles. There is a chance of getting more and more beam radiation. And when we have a cloudy sky or cloud covered with or the sky atmosphere covered with aerosols or smog or fog, diffuse radiation would be received most of the time, and that comes from the entire sky. Reflected radiation comes mainly from the grounds and surroundings, and the key factor governing is the ground albedo or like what is the composition of the ground, whether it's a grass, whether it's a snow or sand or water, depending on it, different reflectivity will be there for the radiation. Now, before I move to the types of surfaces like horizontal surface or tilted surface, let's quickly define tilt angle. We had seen this angle beta while we defined the angle of incidence for solar radiation, that is theta. Okay. So, it is defined as the angle between plane of the solar collector and the horizontal ground surface, which can be adjusted to maximize seasonal or annual energy collection. So, if this is the horizontal surface and if this is the surface which is receiving the solar radiation, this angle made with the horizontal is called as tilt angle. So, for a horizontal surface, beta will be 0. For a vertical surface, beta will be 90 degree, and anywhere between that it is called beta. Okay. So, optimal tilt, what is the optimal tilt angle? Okay, because solar collectors or solar panels, when we put it on the rooftop of our houses, you might have seen that almost all the panels are kept at a similar angle. What is that angle? So, optimally, or there is a thumb rule, it is often equal to the latitude of the location to maximize the annual energy yield. Because like say Roorkee, it's 29 degree north. So, all the solar panels, if we do not know the accurate tilt angle, we can keep it to 30 degree in facing south. So, thumb rule is typically in winter we have to add 15 degree to the latitude, that is phi, and in summer you can subtract 15 degree from the latitude. So, now let us take example of Roorkee, which is at say 29 or 30 degree latitude. So, if you add in winter 15 degree to it, it will be close to 44 degree, and in summer if you subtract, it will be around 15 degree. So, less the tilt angle, more horizontal would be the surface, and in summer, since sun would be available for most of the time of the day, we would prefer to have a flatter horizontal surface compared to a tilted surface. In winter, sun would be available for short duration, so we can have steep angle of tilt facing the position of the sun. Okay. So, that is why this 15 degrees added or subtracted in winter and summer. But to make these changes, the surface should be flexible. We should have an axis beyond, like with which we should be able to move the panels. But in case if it is not feasible to change the position of panels or collectors every now and then at many locations, there ideal or optimal idea would be to just keep it equal to the latitude. Okay. So, we do not change it by plus minus 15 if it is not possible, but then we keep it somewhere in the middle, and that comes out to be the latitude. So, that was the last angle which was remaining, it is tilt angle. Now, looking at direct and beam radiation. So, how does it vary on different surfaces? Let us consider first horizontal surface. This is our surface, and that is the position of the sun, and what we are getting from the sun is the normal radiation, that is IBN. This which is received on the surface is the beam radiation. Okay. With respect to the surface, we are receiving beam radiation, and since it is coming from the perpendicular, the angle between the vertical and the position of sun is called as zenith angle, right. But now for a tilted surface, when the surface is tilted at angle beta, position of sun is similar. With respect to the surface, whatever is received in perpendicular is beam radiation, whatever is received directly from the sun is the normal radiation, like IBN, and the angle between incident radiation and the normal to the surface is the angle of incidence, right? That is what we had studied earlier. Angle of incidence is the angle between solar radiation and normal to the surface. Now, this normal is 90°, but it is not the zenith position. Hence, the horizontal surface, when we calculate IB, like if we take the cos theta, so if we complete this right angle triangle, this is theta z. So, cos theta z would be adjacent side by hypotenuse. Similarly, here it will be cos theta, this because this will be a right angle triangle and this is theta. So, cos theta would be IB by IB. So, you can see for horizontal surface beam radiation is IB and cos theta z. This is the normal radiations, and for tilted surface it is IB and cos theta. So, this is governed by the zenith angle, and this on tilted surface beam radiation is actually a function of angle of incidence, which is a function of several other angles governing the position of sun in the sky. What is angle of incidence? Angle between incoming sun rays and normal to the surface. So, this is known to you. IBN is called as direct normal irradiance. In the next slides, when we learn about solar radiation measuring instrument, we will see that it is actually this DNI, IBN, which the equipments are measuring. Okay, and then we have to convert that IBN to IB using this formula, depending on whether the surface is horizontal or surface is tilted. Now, there is something called as tilt factor, which correlates the different types of radiation received on different types of surfaces. Okay. So, before that, let us see how do we calculate total global solar radiation on a horizontal surface and on a tilted surface. So, horizontal surface, it is just beam plus diffuse, that is the solar radiation, this is horizontal surface. So, you have this direct beam radiation, some diffuse radiation coming, some reflected radiation is not coming on this surface. Okay. So, for horizontal it is just IB plus ID, and for a tilted surface I had just mentioned something about tilt factor. So, it is all three radiations multiplied by their particular tilt factor. So, this is tilted surface, it receives direct, diffuse and some reflected portion also. So, these RB, RD, RR, they are tilt factors for beam radiation, diffuse radiation and reflected radiation respectively. Okay. And each of those tilt factor are defined for each of the radiations as the ratio of total radiation on a horizontal surface by that particular radiation on a tilted surface. And this reflected radiation, it depends on the property of the ground or the surface which is reflecting that radiation, rho. So, IR is nothing but total radiation which is falling on a horizontal surface. What portion of it is reflected? So, it is IB plus ID into rho, that gives you reflected radiation. Tilt factor, ratio of a type of radiation falling on a tilted surface to that particular type of radiation falling on a horizontal surface at the same location and time, that is called as tilt factor. Okay. So, if we have to write it in terms of formula, RB is cos theta by cos theta z, that is what we had seen earlier. For tilted surface it depends on angle of incidence, for horizontal it depends on zenith angle. So, cos theta by cos z. RD, 1 plus cos beta by 2 and 1 minus cos beta by 2 is the reflected. Okay. So, we won't go into the derivations of these formula how they come, but for diffuse and reflected the only governing thing is the tilt angle, that is beta, and for RB it is a relation between cos theta and cos theta z, and both of these relations when expanded will include beta in it along with other angles. Okay. So, let us look at the tilt factor for beam radiation. We can expand it using the formulas given in the book based on solar geometry. So theta is angle of incidence, theta z is zenith angle. Now this equation, which is given by cos theta z, it is theoretically correct, but for actual field calculations, it is difficult to measure the angle of incidence directly. Hence, we need to expand it using other fundamental solar coordinates, which depends on latitude, declination, tilt angle, surface azimuth and hour angle. So, using that expanded formula of cos theta. Now, for horizontal surface, beta is 0 and theta is equal to theta z. So, cos theta is equal to actually cos theta z for horizontal surface. So, when we substitute this, we get cos theta z in the short form, because when the moment you substitute beta is equal to 0, sin beta terms would go cancel out, cos beta terms would turn out to be 1, and then it can be reduced to this short form. That is the cos theta z. Now, for northern hemisphere, where all the solar panels or collectors are facing south, gamma is 0, right? The surface azimuth angle is 0. So, if you substitute gamma as 0 in this equation again, so here the sine terms would get cancelled and cos gamma terms would turn out to be 1, and using again those trigonometric formula of sin a plus b or cos a plus b, we will get the reduced version of cos theta. So, having that reduced version of cos theta as numerator and cos theta z as denominator, you can calculate RB. RB is nothing but tilt factor for beam radiation. So, in a given numerical or for a given location, a time, so for a given location means for a known latitude and given time and date. So, time and date would give us hour angle and declination angle, and the type of surface, whether it is tilted or not, it will give us angle of beta. So, once all those angles are known, here we can easily calculate tilt factor for beam radiation. And then for tilt factors for diffuse radiation and reflected radiation, what we need to know is only the tilt angle. So, once we have all these angles along with tilt angle, we can calculate RB, RD and RR. So, we will look at how that formulas add up, but one question, like we have been saying, like in the northern hemisphere all the solar panels and collectors face south, but why do they face south? In previous lecture we studied, irrespective of the hemisphere, whether it is a north or south, solar sun rises in east and sets down in west, right? But what happens, position of sun in the sky, it changes every hour and every day. Okay, like let us take example with this figure. Here east to west is given, where sun is rising in the east and going to the west. But as the months changes, this inclination, it goes on towards south for northern hemisphere, and then it starts coming back for another 6 months till the overhead point, like the line which is exactly above east and west line. Okay, it will never cross this line, so it won't come in this hemisphere, it will stay here, but it will be inclined always towards the south. For first 6 months it will go on this side, and for next 6 months it will come back again on the overhead point between east to west. And that is the reason why sun is always in the south, and all the collectors or panels which are there in the northern hemisphere, they always face in the south direction. The sun is higher in the sky in summer than in the winter, and it moves daily in an arc across the sky, reaching highest point at noon. So, this is the highest point, okay, which happens at noon. But this inclination towards the south keeps on changing. For 6 months it goes on towards south, for 6 months it goes on coming towards the overhead point, it never crosses towards north. So, that is why all the collectors or panels in the northern hemisphere, they always face south. Now, Since we had calculated RB, RD, RR, all three formula. For horizontal radiation, IB like plus ID, okay, and for a tilted surface, it will be IB plus ID plus IR, but then you multiply by tilt factors of all three, okay. So, total radiation intensity which is falling on a tilted surface is, okay. Now, since we have been talking about hourly radiation or instantaneous radiation, we use the symbol I, but if you are talking about daily radiation, most of the books will go to for the symbol H, okay. So, H, you use H or I, does not matter, but be clear and stick to one consistent nomenclature. So, HT is HBRB plus HDRD plus HRRR, but that HR is nothing but H into rho, where rho is the reflectivity. And if you substitute the values of RB is calculated by this formula, RD and RR. So, using this formula we can calculate the total radiation on a tilted surface. So, what we need to know is the location. Location is phi, latitude, the type of surface, or what is the tilt angle beta, then the date and time, that will give us delta and omega. So, these are the four things that are required, because those are the missing terms: phi, beta, delta and omega. So, we are talking about northern hemisphere, panels facing south. So, once we have these four things for a given location, date and time and the tilt angle of the surface, we can calculate the tilt factor for each type of radiation, and based on the radiation data we can calculate the total radiation using this formula. Clear? So, let us try to do one simple numerical where you make use of the same formula, so that it is more clear. On 29th March 2026, so it is a date which is given to us in Roorkee. So, latitude is given. Global solar radiation, global means total radiation, right, 900 at 13 p.m. Since time is given to us, we can calculate omega. Find the total solar radiation intercepted on a tilted surface, beta is equal to 10. If there is a tilted surface at 10 degree installed, assuming 80% of radiation is beam. So, now total radiation is given, out of that 80% is beam radiation. So, IB is known to us, reflectivity of ground is 0.1, reflectivity is also given to us. So, how do we approach this problem? But let us put down the given numbers. So, that is the date 29th March 2026. What will be the value of N? N would be 31, 28, 29, 9, 9, 18, 2, 2, 4, 3, 7, 8. Okay. So, N is 88 for the date 29th March 2026. Latitude phi is given 29 degree, it is fine. Beta is 10. Now, next thing is omega. So, time is given 13. So, omega will be 15 into 13 minus 12. So, it will be 15. Okay. So, omega is 13 minus 12. Now, out of the total radiation 900, 80% is the beam radiation. So, beam is 720 and remaining would be the diffuse radiation, that is 180. So, let us assume that this is at a horizontal. Okay, global horizontal solar radiation is given. So, on horizontal we won't have any reflected part. So, this 900 is nothing but addition of IB plus ID, and we have calculated IB and ID. Now, when we set up a tilted surface, then we may get some portion of reflected radiation. Okay, that is where we will add reflectivity. Now, since the date time is known, we can calculate the angle declination delta using this formula of n minus 81. It comes out to be 2.8. Now, all the unknowns in the formula for RB are known to us. Okay, phi, delta, omega and beta. So, we can calculate RB by substituting those values and we get 1.1. So, that is the tilt factor for beam radiation. Now, what is the formula for total radiation? It is IBRB plus IDRD plus I rho RR. Now, beta is known to us. If you substitute these values, IB is 720, ID is 180, then I rho. So, total radiation on horizontal surface is 900, out of which 0.1 would be reflected. Okay, so that is I rho and 1 minus cos beta by 2. Beta is 10 degrees is given to us. So, if you do the addition, it comes out to be around 950 watt per meter square. So, this is going to be the total radiation intercepted on a tilted surface. So, are you able to make it like when we have like on a horizontal surface, it is 900, but on a tilted surface, we get higher than 900 because of the additional component of reflected radiation, also because of the effect of tilt angle, which is accounted by RB, RD and RR as a portion which is multiplied by each type of radiation. So, this is how you can calculate the total solar radiation for a given place, for a given date and time. And if we know the either one of the type of radiations, either total radiation or beam or diffuse. Now, there are different equipment or instrument used for measuring solar radiations. So, since there are different types of radiations, there are different types of instruments which can measure different types of radiation. So, we have basically two types of radiation, beam and diffuse, which needs to be measured. So, for this is the first equipment called as pyranometer. It looks like a small plate with a globe on top of it and with the black thermophilic material at the bottom, and then it is connected to a wire which generates voltage and cause current to flow. And second equipment is parallelometer. The way you can see this equipment is designed, on the radiation passes through this telescopic tube. So, it is clear that this is used mainly for beam radiation, and since it is a globe, it will receive radiation from all the angles. It is typically used to measure global radiation, which is beam plus diffuse, whereas parallelometer is used to measure beam radiation. Now, this is actually tracking the path of the sun. This whole assembly is made in such a way that this equipment keeps on rotating with the position of the sun, so that every time it is only the beam radiation which passes through this parallelometer. But this parallelometer, it measures beam radiation, but it does not give actual beam radiation. It actually measures the DNI, direct normal irradiance, or in that formula, if you remember, for cos theta and cos theta z, IB was IBN cos theta or IBN cos theta z. So, if we know from this equipment IBN, and if you know the position of sun, whether its angle of incidence or its zenith angle, we can calculate beam radiation, right. So, that is what the job of parallelometer is. But now, how do we calculate diffuse radiation? So, in that case, since pyranometer is not like tracking the position of the sun, but what we can do to block the beam radiation from falling on the pyranometer, we can have a shading ring. This is a shading ring. Its job is to block the beam radiation from the sun and it prevents those beam radiation from falling on the surface of the pyranometer. So, what it measures is only diffuse radiation, because the ring is blocking beam radiation and this ring keeps on tracking the position of the sun. As the sun moves from here to here, the ring also moves along with the sun, so that for entire day whenever measurement is made, it is blocking the beam radiation, so we can get diffuse radiation. So, if we have to calculate or measure both beam and diffuse radiation, we will have to put two pyranometers in series. So, one pyranometer can give us total radiation. The pyranometer with shading ring can give us diffuse radiation. If you subtract diffuse from here, we can get beam radiation. And if we need accurate DNI, like direct normal irradiance, and then calculate beam radiation, that is the second type which we can get from the parallelometer. Okay. So, now let us look at the working principle of these two equipment. The working principle. So, both pyranometer and parallelometer have similar working principle, like it has a glass dome at the top, the radiations like penetrate through this glass dome and then it falls or it gets absorbed by a thermophile or a thermophilic material which is typically black in color, a good absorber, and then that thermophilic material is like connected to a reference surface which generates like temperature difference and it generates a small voltage. Similarly, in parallelometer also we have this glass window through which beam radiation enters, and at the bottom of the tube we will have a thermophilic material connected with a reference surface below it, and this black surface, because it absorbs a lot of radiation and becomes hotter, the reference surface below that black surface is at a lower temperature, and that difference in the temperature, it generates a small voltage in both of these equipment, and that voltage causes current to flow, and then accordingly the readings are converted to the radiation value. Like if you remember those values of H equal to I square RT, the heat is depending on the current and voltage, right, VIT. So, V is equal to IR by Ohm's law and you can get I square RT in joule. So, now this effect is also called as Seebeck effect. It was proposed by Thomas Seebeck in 1921, which is actually the direct conversion of temperature difference into voltage. It typically happens when, like say, two dissimilar conductors or two dissimilar semiconductors are joined in a loop. Okay, when they are joined in a loop and there is a temperature difference between the junctions. Okay, between the junctions of those two dissimilar materials, if there is a temperature difference, that temperature difference induces some voltage or potential difference which actually causes current to flow. That is called as Seebeck effect, proposed by Thomas Seebeck in 1921. On the same principle, these two equipment, pyranometer and parallelometer, works, converts the absorbed heat into temperature difference into voltage, voltage to current, and accordingly the radiation data can be calculated or measured. Other than these two sophisticated equipment which are most commonly used in present world, there is a old equipment called as sunshine recorder. Like this is a picture of one of the most widely used Campbell-Stokes sunshine recorder, originally developed in 1858 by Campbell, and later a modified version of this was developed by Stokes in 1879, and many times is referred to as Campbell-Stokes sunshine recorder together. What it does, you can see like glass sphere here at the bottom, and then there is this curved plate on which these cards, it is called as solar card or sun card. These cards are placed so that with the positioning of the sun, as the sun moves from east to west, the amount of radiation being like concentrated through this glass sphere on this recording sun card, because of its focal point, it starts burning the card, and the length of the burn, it will tell us the amount of or the duration of sunshine. But the problem with this method was it's approximate, and these cards needed to be replaced every day. And there were some approximate guesses where you can make an inference, like when the card has got the complete hole, it means that time the sun was at its peak, and many times the card will just turn blackish. So sun was not at its peak, but there was some radiation, and at some point of the time, some portions of the card, they are not at all affected. So it means there was hardly any beam radiation going through it, and most of it is diffuse. So it was approximate way, but still it got very famous, like because it was developed almost 180 years back, and now it is being kept in museums for samples. But most of the measurements that we do in present world are from pyranometer and parallelometer. So that was all about the equipments or the instrument that can be used for measuring solar radiation. So to summarize, what we covered today was types of solar radiation. So mainly three types. What were those? IB, ID, IR. Beam radiation, diffuse radiation, and reflected radiation. On horizontal surface, we get only these two. On tilted surface, we get all three, but then we have to include the tilt factors for each of these three types of radiations. And then we saw how we can calculate the total radiation falling on any horizontal or tilted surface. The only thing is, for RB, it depends on 4 parameters, which is the location, date and time, and the tilt angle. Once we get these 4 values, we can calculate RB, and using beta value we can calculate RD and RR. From the given solar radiation data, we can find the total radiation on a tilted surface. Then in the measuring instruments, we saw pyranometer, which is mainly used for global radiation or total radiation. Global means diffuse plus beam, but if we add a shading ring to it, we can measure only diffuse radiation, because shading ring will block the beam radiation. So if we use 2 pyranometers, one without ring and one with ring, we can get all 3 types of radiation, that is total radiation, beam radiation, and diffuse radiation. And if we want only beam radiation, we can use parallelometer, but again it does not give us IB, it gives us DNI, the normal beam radiation, and from that, using cos theta or cos theta z, we have to calculate IB for tilted surface or horizontal surface. Okay, but the working principle for both of these equipment was similar, based on the Seebeck effect, where temperature difference creates a voltage, and that voltage causes current to flow, and which is calculated as a radiation or a radiation energy. And the last one was the Campbell-Stokes sunshine recorder, which makes use of sun card, which gets burned because of concentrated sunlight. So that's all for this lecture, and from the next lecture onwards, we will move towards the conversion and utilization of solar energy using 2 approaches. One is solar thermal, other is solar PV. So we will be starting with solar thermal. Thank you.